In this video, we're going to do a few more examples involving geometric sequences. So remember, a geometric sequence can be defined recursively. So you have a first term, and then to get to each subsequent term, you just multiply by a common ratio r. So you take the term before it and you multiply by r, and that gives you the next term. Okay, now in example 3 here, we wanted to determine whether or not this sequence is geometric. So you might think, okay, let's try Tn over Tn minus 1. So that's going to be 4 to the n minus 1 over 4 to the n minus 1 minus 1. Okay, now because of the minus 1s, I can't actually simplify, so they don't cancel. So I don't see anything I could do here. So what I might want to think is, okay, what do these terms actually look like? So T1 is 4 to the 1 minus 1, so that's 3. Okay, now T2 is 4 squared minus 1, so that's 16 minus 1, so that's 15. So to get from T1 to T2, I need to times by 5. Okay, so then T3 is going to be 4 cubed minus 1. So that's 64 minus 1. So that's not 64, 63. And 63 divided by 15 is 4.2. So to get from here to here, I need to times by 4.2. So because these are not the same, okay, I'm not multiplying by the same number each time, so it's not a geometric sequence. So that is enough to say that the sequence of t to the n, tn's is not a geometric sequence. Okay, so I tried to show it's geometric, wasn't working out, so I just wanted to see what the terms look like, and it turns out that I don't always multiply by the same number to move forward. Okay, now in a geometric sequence, you can simplify, using the recurrence, you can simplify and easily come up with this closed form formula. So the nth term is the first term times the ratio to the power n minus 1. Okay, so if I wanted to find the 8th term in this sequence, so A1 is 1. Now, to get from 1 to 3, I multiply by 3. To get from 3 to 9, I multiply by 3. So my ratio, you could also do r as 3 over 1, like dividing the two terms. Okay, the r is going to be 3. So then A8, so the 8th term, is going to be the first term times the ratio to the power 8 minus 1. So that's going to be 3 to the power 7, which is 2,187. So that's my 8th term in that sequence, assuming that it continues in the same manner. Okay, now for example 6 here, they tell me that A2 is equal to 7. Okay, and R is equal to 1/3. So if I want A1 is actually going to be A2 divided by R. So maybe I should show you why that's the case. Okay, so R is equal to A2 over A1. So if I want to solve for A1, because I'm going to need the first term, I'm going to have to multiply both sides by A1. So that gives me A1 times R is A2. And then if I divide by R, I get A1 is A2 over R. Okay, so that means that A1 is 7 divided by 1/3. So that's going to be 7 over 1 times 3 over 1. I flip the bottom one and multiply. So A1 is actually 21. Okay, so that means that the nth term is given by the first term times the ratio to the power n minus 1. So that would be our formula giving the nth term. Okay, so we wanted to be careful because they did not give us a1, they gave us a2. So then we needed to figure out what a1 is. Okay, so when we want the partial sums, so the sum of the first n terms, we can compute it using this formula here. Okay, so the first n terms is the first term times 1 minus r to the n over 1 minus r. Now this is as long as r is not 0 or 1. Okay, for these terms, then the sum is easier to compute. Okay, so if r is 0, then it's only the first term, for instance, because you multiply by 0 each time. So all the terms are going to be 0 except the first one. And for 1, you're going to have the same term over and over again. So again, easier to compute. So let's say we want to find the sum of the first 16 terms of this geometric sequence. Okay, now we did see this one before. So for this sequence, so a1 is going to be 4 over 3 to the 1, so 4/3. Okay, and the r is going to be a2 over a1, and a2 is 4 over 3 squared, okay, over 4 over 3. So that's 4 over 9 times 3 over 4. The 4's cancel out. So it's 3 over 9, which is 1/3. Okay, so my first term is 4/3. My r is 1/3. So then if I want s to the 16, it's going to be the first term times 1 minus 1/3 to the 16 over 1 minus 1/3. Okay, now if you compute this, so we could simplify it a bit. Okay, so 16, 3 to the 16 is probably a really big number. Yeah, so let's just leave it like that. So it's going to be 1 minus 1 over 3 to the 16. Down here I have 2/3. So I could flip that denominator and multiply, and I'm going to multiply up at the front because it doesn't matter. Okay, so the 3's cancel out, and in fact 4 over 2 is just 2. So this is 2 times 1 minus 1 over 3 to the 16. Okay, so if you compute that, okay, it's going to be approximately 1.9. Okay, so how many 9s? 1, 2, 3, 4, 5, 6, 7 9s. So 1, 2, 3, 4, 5, 6, 7, and then a 5, 4. Okay, so very close to 2. The reason why I don't want to write 2 is because it's not exactly 2, and we already looked at in the first video, the infinite sum of this sequence is 2. Okay, so you can see how close it gets to 2 when you're at 16, and it just keeps getting closer and closer and closer. So that means that you just keep getting more 9s here as you get further along. Okay, so here, this is an Sn. Okay, so it goes from 1 to n. Okay, now here it's written in the sequence. Okay, so this sequence, when k is 1, is just 4. So a1 is 4. And then each time I multiply by 3. Okay, so the r is 3. Okay, so that is a geometric sequence. So this is going to be 4 times 1 minus 3 to the n over 1 minus 3. Okay, so you could simplify this. 1 minus 3 to the n. Down here I have a negative 2. So 4 divided by negative 2, so this is going to be negative 2 times 1 minus 3 to the n. Okay, so that's what this sum is equal to. Okay, so it depends what n is, but that's how you can compute your sum. Okay, so now for the infinite sum, if your r in absolute value is between 0 and 1, so your r is between negative 1 and 1, I guess I should write and not 0. Okay, then you can use this formula, so the infinite sum converges to a number. Okay, so here, so again, we're computing an infinite sum, so the sum goes from 1 to infinity. Okay, and this is my sequence inside. So when k is 1, this is my first term. Okay, that's going to be negative 2/3 to the 1 minus 1. So negative 2/3 to the 0 is just 1. Okay, so a1 is 1. Now if k is 2, my a2 is negative 2/3 to the 2 minus 1. So it's negative 2/3. So that's enough to tell me that my r is negative 2/3, which you might have already guessed. Okay, so then my, in absolute value, r is less than 1. So this sum does converge. Okay, so that means that this sum of negative 2/3 to the k minus 1 is going to be a1, so that's 1 over 1 minus the r value, which is negative 2/3. So that's 1 over 1 plus 2/3, which is 1 over 5/3. So it's going to be the flip of that, 3/5. Okay, so this sum actually equals 3/5. Okay, so that's what it approaches as you take more and more and more terms. Okay, so those are some examples of geometric sequences.